And let's go from current slide. And let's even turn on the projector. But while the projector is coming on, let me make this one other announcement. And I don't know if any of you would ever want to come by during my office hours. I have almost no office hours on Mondays and Wednesdays. I have 30 minutes from 8 to 8:30 and 35 minutes from 5:25 until 6 o'clock. That's all, folks, because other than that, it's 5 minutes between the classes, and that's it. So on Tuesday and Thursday, though, I have big blocks of office hours from 10:45 until 4:30, Tuesday and Thursday. I have an 8:30 class, and I have a 5 o'clock class, but it's over on another campus, so I have to allow 30 minutes to get there. But if you were wanting to come see me during office hours, I will be here tomorrow, knock on wood, all day long. But on Thursday, I will not be on either campus at all. I have cataract surgery scheduled for Friday, and usually they start pretty early in the morning, and even though they don't take all day, you're kind of out of commission all day. There's not much, and in fact, even the next day, they don't want you doing very much, but that's Friday, and I won't be on campus anyway then either. So anyway, Thursday, I will not be on campus at all. All right, now, if my memory is right, and there's no guarantee it is, we did example 4, right? But I had missed noting that example 3 was skipped on the slide set. Usually they do the first one and not the second. This one they skipped the first and did the second. So I'm going to do example, or will at least attempt example 3 will be where we'll be going from today. But before we do, any questions from anything we've covered so far? None? Okay. So this is page 488 for those who do have a book and are following. Moving a space module into orbit. Okay? A space module weighs 15 metric tons on the surface of the Earth. Now that, I don't like that statement at all as a physicist, okay? But this is going to be such a bizarre problem. So let me go on and write it down the way they're saying it, okay? Here's what I don't like about it. I guess I ought to go on and tell you that. What is a metric ton? Does anyone know? I'm sorry? A little louder. Is it 2,000 pounds? Okay, that's approximately. Okay. Let me back off a moment. A U.S. or English or whatever ton, a standard ton, is 2,000 pounds. That's what you were saying. A metric ton, though, is not. A metric ton is close. That's why they call it a ton. In the metric system, we usually use kilograms, not pounds. But kilogram measures mass, not weight. So when it says it weighs this many metric tons, I know what they're trying to say, but it's really lousy choice of words. Okay, it should say it has a mass of 15 metric tons. Because what a metric ton is, a kilogram is a unit of mass. Well, this book would probably be a couple of kilograms maybe, but it's a certain mass. Okay, that's 1,000 grams, right? Kilogram. Okay. 1,000 kilograms is 1 megagram. That's what they call a metric ton. Okay, so it's technically a mass measurement, not a weight measurement. That's the first thing that bugs me about it. But they say it weighs as many metric tons. Now, the reason they say metric ton, and again, this is not an exact thing, this is an approximate thing. A kilogram, a mass of 1 kilogram is about the weight of 2.2 pounds, okay? And they'll give that as if it's a conversion. 1 kilogram is 2.2 pounds. It's not. A kilogram measures mass, a pound measures weight. That's like saying an apple is 3 oranges, you know. No, it's not. I mean, it might be equivalent in no, you have to do an awful lot of maneuvering. So, 1,000 kilograms is 1 megagram. They call that a metric ton. Why? Because if 2.2 pounds is a kilogram, then 1,000 kilograms would be about 2,200 pounds, which is just a little bit more than a ton. So it's 2,200 pounds is a metric ton, 2,000 pounds is a standard ton. If you're counting for, and of course now we're always assuming on the surface of the Earth, because once you leave the surface of the Earth, your weight decreases, but your mass stays constant. Okay. And there's even problems with that in this problem. But let's deal with it. So that's the first thing that sort of bugged me here. It doesn't weigh that. It has a mass of 15 metric tons on the surface of the Earth. How much work is done propelling the module to a height of 800 miles above the Earth? So, see, I don't even know what to write down as my things here. I want to put the mass, and I'm going to put it this way, and it may change. The mass of the spacecraft, space module, is 15 I'm going to put megagrams, which is the same as metric tons, okay, on the surface of the Earth. How much work is done propelling the module to a height of 800 miles above the Earth? So we're looking for work. Okay, that's the unknown here. Get that out of there. Oh, and by the way, I can't remember if this was happening last Wednesday or not, but my computer cord, I think it had happened, but it didn't happen in this class. My computer cord doesn't always make good contact with the plug, and sometimes I'll lose power, so every now and then, especially if I see this modulating some, I look down here to see if something is happening here. Looks like so far it's doing well. But last time on Wednesday, by my third class, Cal 3, it started just doing all sorts of weird things. And this morning when I first let it off, I had to hold it in place for several minutes before it finally would stay on. I don't know. I think it's a heat issue too. I think something expands a little bit once it heats up a little, and it does better. So why it messes up at the end of the day, I don't know. Okay. How much work is done propelling the module to a height of 800 miles above the Earth? So we're ultimately going to do, I'm going to call this our S max, okay? The maximum height is going to be 800 miles. Now, if the fact they were calling this a weight was not enough, now we're going to be dealing with U.S. customary measurements here and metric measurements here. This problem is really, but this is real life. It's all screwed up because it's mixing all these things together. So we're going to have to sort them out at some point. Okay. Now they have a picture in the book. I guess I'm going to have to draw it. And it says use 4,000 miles as the radius of the Earth. And the reason they say that, let me draw the Earth here. Now that's not a very good drawing. I'll try to make it look more like a sphere. Okay. Now, from here to there is 4,000 miles. So they're sticking with their U.S. customary. And they're trying to get it from 4,000 miles to 4,800 miles. So here's going to be where it ends. So this is 800 miles from the surface of the Earth. Okay? Get out of there. Okay. Now, do not consider the effect of air resistance or the weight of the propellant. Two really big things you're completely ignoring. So we don't have a variable mass, which was afraid when I first read it that this is going to have to be written as a variable mass. We're going to assume it's not. Okay? So I'm just going to make a guess here. Maybe they really mean just the module, the space module, not the whole rocket and everything else, because the rocket's going to be losing mass as you go. So we're not doing that. Just the work needed to get the space module, which is not going to be losing any mass because it's not propelling itself yet, 800 miles away, 800 miles up. Okay, and we're not going to consider air resistance. I bet you NASA wishes they didn't have to. Okay. Now, because the weight of the body varies inversely as the square of the distance from the center of the Earth, the force exerted by gravity is, this is the force as a function of distance. I almost want to call it R, but they're using X, so I'll do X is the distance from the center of the Earth. It'll come back, I hope. Yeah, there it comes. Is equal to some constant time divided by X squared. Okay? Now, big deal about what this constant is, okay? But that's, this is a proportionality, inversely proportional to the square of the distance. So you just put a proportionality constant in here, equals C over X squared. Okay? Without telling you what C is. C is the constant of proportionality. Because the module weighs 15 metric tons on the surface of the Earth, the radius is approximately 4,000 miles, we can know that, and here is where they start making what I consider sort of stupid things. They're saying that is a weight. So I called it a mass, they're calling it a weight. Okay, little w. Because what they say here, the weight, and they're calling that a force, so that's counted a weight, 15 is equal to this C divided by 4,000 squared. A physicist would go nuts over this way they've worked this problem. Okay? All right. So, the square of 14,000 would be 16 million. Okay? Because you double the number of zeros and square the 4. Multiply that by 15. I'm going to take their word for it, that the C would then be, is that even right? Some of you do that. Second? A little out. What did you say?
240 million.
240 million, is that what they got? Okay, all right. That's what they got in the book, too. 240 million. Okay. And what units would that be? Metric ton per mile squared. A really bizarre thing, so I can see why they're not going to put a unit on it. They call it force per distant increment. Getting it, yeah. Okay. So, the increment of work that just gives you the C. Going back up here, then you have the force is equal to keep from writing all that, I'm going to 240 times 10 to the 6th with no units because it's such a bizarre unit over X squared. Okay? It will come back, I hope. Okay, there it comes. Now, your increment of work, that is your force, and over an incremental distance, the increment of work would be your force, variable force, times the increment of distance. So then your delta W would be $240 million times, let's just go and put it over x squared times your delta x, incremental thickness there, okay? So when you integrate that, your work will be, I'm sorry, that's where I would put the 240 million out front. 240 million times the integral, we'll come back to that in a minute, dx over x squared, okay? Which, actually I don't like writing it that way, so I'm going to change it, sorry. X to the minus 2 dx. That's far easier to do an antiderivative for that. Now, where are we going from? We're going from 4,000 miles to 4,800 miles. Okay. Now, your x's is in miles, which makes all these units almost crazy because this is some metric tons per mile squared, you know, so no wonder they leave the units off. But there is your integration that we have to do, okay? So the work is 240 million. That shouldn't be there, whatever. Okay. What's the antiderivative of x to the minus 2? Say again? X to the minus 3, you said? Okay. Remember, when you integrate, it's a plus 1. Yeah. X to the negative 1, but a minus, which is a bit bizarre too, and this is going from 4,000 to 4,800. Whoa, I can't write. My pen is very slow, and I realized I wrote on top of itself. Okay. Now, yeah, believe that's going to be okay. Let's do that part before we multiply this in. That'll be minus 1 over 4,800 plus a 1 over 4,000. You buy that? This with the minus sign here, this over that, minus and minus, which would be a plus 1 over this. Okay. And I think it would be so much easier rather than do it by, you can do it by fractions and things like this, but if you got a calculator, just do this calculation. 1 over 4,000 minus 1 over 4,800. Not a super hard calculation, right? And then multiply that by 240 million. And see what you get.
Did they get negative 10,000?
Say again?
Did they get negative 10,000?
They got 10,000, not negative. Okay. This is a bigger number than that. I mean, I know 4,000 is smaller than this, but 1 over 4, 1 over 4,000 is larger than 1 over 4,800. Yeah, so 4,000. 1 over x, or however you do it, minus 4,800, 1 over x. That should give you not a huge, but a positive number, and multiply that by that. But 10,000 is correct, or that's what they got. 10,000, and their units are miles tons. Oops, not per ton, tons. Yuck. Okay. Which is okay. If you think before, we talked about foot-pounds of work. Miles, tons would be another unit of work. But this is miles, U.S. customary, metric tons. Yeah, it just is a bizarre way to name the problem. But yeah, that's what we got. And then they changed that to foot-pounds by using the 5,280 feet is 1 mile, and a metric ton is, I was saying, approximately 2,200 pounds is 2,205, if you want to be more precise. And when you put all that together, you get an enormous number of foot-pounds. 1.164 times 10 to the 11th foot-pounds, which is why they probably use miles tons, because it's a much handier conversion. Okay, and then they turned around and used SI units, which were joules, and used a factor there to get from foot-pounds to joules, and came up with 1.578 times 10 to the 11th joules. Okay. And at the end of all that, they went back to go over these two things, which we went over in class already. But you see, what we did was doing it with this kind of an implement. Some problems work better if you do your delta F rather than your delta X. Have X being a function with as some function of force and doing your delta F. That's usually not the case, but there are some applications where that would be the case. All right. Kind of a pain in the neck. Kind of. Okay. Now, I think that the next problem, did you see that? That sphere almost fit exactly in my sphere. Isn't that amazing? Okay, never mind. Okay, that was example 4. I don't think they do example 5, but let me see if I can find it. Goodness, 4 was long, wasn't it? Y'all remember that. It was a pain in the neck. Oh, yeah, and they don't do example 5. So let's just do example 5 and 6. But we'll first do 5. Now, this is another one. It always bothers me that I might be losing my power here. Lifting a chain. Now, this is one where you probably will do the other increment. A 20-foot chain weighing 5 pounds per foot. That's supposed to be weighing 5 pounds per foot. Okay, is lying coiled on the ground. Okay, here's the chain here, wad of chain here, coiled on the ground. How much work is required to raise one end of the chain to a height of 20 feet? So you're going to raise this up to 20 feet. Okay, so that is fully extended. Okay, and they show a backhoe doing it. I'm just imagining some unknown force is lifting it up. Okay. Now, in this case, if you go back to I know it's such a long problem that it's going to take a while to back up, but it's going back. There it was. Here, this is a case where I think we're going to be doing a delta F times X, because the length is just going up. But what you're doing is lifting a variable force up a certain height. So this probably is going to wind up being just the easier way to go on this one. I said you don't happen to use it much, and here they came and gave us an example to prove me wrong. So, okay, so here's what we got. All right. Oh, wasn't even on the right page there. Okay. How much work is done to raise one end of the chain to a height 20 feet so it is fully extended? Okay. And here's what we're going to do. We're going to assume incremental lengths of the chain. Not literally down to lengths, but incremental, not lengths of the chain, but lengths of the chain. And what we're going to do is lift each of those however far we need to lift it. Okay? The weight of each section is then an increment of force. Okay, of course, weight is force. So let's just take a representative length here. Okay. And this is going to be a dy. They let y be the variable going up, which is pretty common. Y is going up. So little incremental length here is a delta y. Okay? Now, because they're 5 pounds per foot, if delta y is measured in feet, then this would be 5 delta y would be our incremental, Didn't take, okay, there we go. 5 delta y would be the incremental weight. So let's call that our incremental force. 5 delta y is the incremental force. 5 pounds per feet and delta y feet. Okay, that you've listed it. Okay? Now, that's the incremental force. Okay? The incremental work would then be the force times the displacement. Well, what have we displaced it? We've displaced it y units up. Now, y isn't the total. That's just, if it was from here to here, the y is how far we displaced it from the ground. So it would be y times 5 delta y. That would be the incremental work. Okay? And you're going from y is equal to 0 up to 20 feet. So that's your integral. The total work would be the integral. Let's take the 5 on the outside. The integral from 0 to 20 of y dy. The delta ultimately goes to a dy. Okay? Now that's a pretty easy integral to deal with, right? What would that be? Can't believe it's that easy though. Yep, it is. Okay. 5 antiderivative of y dy. Y squared over 2 evaluated from 0 to 20, which would be 5 times. Now, 20 is not too bad. 20 squared is 400 divided by 2 would be 200. I'll do the 0 part. Done. Okay. And that would be 1,000 foot-pounds. make sure my units are right. Yeah, 1,000 foot-pounds of work is what it would take to lift that chain 20 feet into the air. 1,000 foot-pounds. Now, again, all the hard part is setting up the problem. The calculus is the easy part, taking and how to do it. Getting all this, making sure you've got this designated properly and going along here. And in this case, it's one of those that the force is the incremental part. The distance is just a linear thing. You're taking it up there. Okay, now. In the next example, we'll consider a piston of radius r. Any questions on this one before we go? That turned out being a lot more straightforward and simpler than I thought it was going to be. Any questions about it, though? Les, I think I'm going to need my space for this one too, because not everybody has a book. I'm going to have to do a fairly ugly drawing here, and you're act surprised because none of my drawings are ever ugly. No, never mind. Okay. Next example, you'll consider a piston of radius r in a cylindrical casing, and that's where they have a figure here, and you don't have the figure. So let me see if I can give it some sort of rendition here. Let this be your casing here, and this is a cylindrical type opening here. Okay. Now you got inside here a piston going from here to say there. Okay, so this is your piston, and here is your gas back here in the back. Okay. The piston has a radius of r, little r. As the gas in this cylinder expands, the piston moves and work is done, because the exploding gas or whatever is happening to the gas here, pushing the piston forward, that's what's doing work. Okay? And they draw this as your X, and seems like to me it'd been better to draw your dx there, but they just did an x. So rho is the pressure of the gas, and there's nowhere in the picture to show this. So rho is the pressure of the gas. And the pressure, by the way, is usually in terms of pounds per square inch, or some sort of work per area. Okay, pounds per square inch or whatever. They're using pounds per square foot. Okay, against the piston head, V is the volume of the gas in cubic feet. Then the work increment. Okay, so this is the pressure of the gas, and this is in pounds per square foot. Okay, the volume of the gas here is cubic feet. Okay, that would be in cubic. I probably should put equal, but volume in cubic feet. Okay. Then the work increment involved in moving the piston delta x feet. So we're going to do from here to there is our delta x. So the work done in moving the piston that far will be your delta x feet. The work to do that is your delta w. Delta w would then be, and remember, it can either be F delta x or x delta F. In this case, we're set up to do a delta x. So we'll let that be the variable over which we're going to be integrating. and then we got to figure out everything else in terms of force, in terms of that x. Okay. Now, where do you get the force? Well, the force is in pounds. Okay, and the only place that comes from is pressure. Okay, so you would have to take the pressure of the gas times the area. So force equal, okay, maybe I should write it this way. Pressure is equal to force per unit area, so force is equal to pressure times unit area. Okay? Now, we've got, okay, I'm drawing something wrong here. I put a rho here. They're using P for pressure. So this is a P. That's a P. Okay, I misread it. Cataract. I'll blame everything on that for a couple more days. Okay. So whatever that pressure is times the area. Well, what's the area of that piston? Here is your radius here. The area of that piston is pi r squared. So this is P, that's a P, times pi r squared. Okay? Now, your dx has nothing to do with the radius or anything else. But if you multiply that by your dx, that then gives you your force F dx. That would then be, this is your F here times your dx, or delta x. Okay? Now, that's going to be the thing that we integrate. But now here's a problem. This radius here is fixed. That's not part of your variation here. And so far they haven't given you enough information. What is it you're really doing? Are you really measuring along your x, which is the length of expansion there? They tend to indicate not that it's a volume problem. Okay? And this pi x squared, r squared, I'm sorry. I'll put the x in there. Pi r squared dx, that happens to be your volume of that cylinder. Pi r squared is the area, delta x is the amount it's expanding, so that's your volume. So this is your dV. Okay? Now we're getting somewhere that we perhaps can fiddle with this. So another way of expressing this work is the pressure times the incremental volume. Okay. All that was just to get us to that point. Okay. Again, that's a P. Even though I draw it like that, it's hard to see that that is a P, not a rho. Okay. Now, your increasing volume as the volume of gas increases from V0 to V1, so the work is done in moving that. So then you would have your work to be the integral from V0 to V1. I just said it, but I couldn't remember how they expressed V1. You can bring the pressure out front as long as it's constant, dV. Okay, and that's a pretty simple integration to do. I'm sorry, they can't do that because the pressure is also a function of volume. Sorry, the pressure has to stay on the inside. And how pressure is related to volume, it's an inverse relationship. So it's the integral of, what they use K, V0 to V1 of K over V dV. Okay, so there's a formula. Now this is all just to set it up so we can work the next example. So that's where we're heading from and to, with no numbers whatsoever in it. So example 6 gives us the numbers, and we don't have room to keep this, so hang on to the thought and let's go from there. Now, a quantity of gas with an initial volume of 1 cubic feet, so your V0 is 1 cubic foot of gas, and a pressure of 500 pounds, P0 is 500 pounds per square inch. Yeah. I want to write that P, well, no, I'll put pounds per square inch. Okay. PSI is a quicker way to write that. To a volume of 2 cubic feet, okay, find the work done by the gas assuming the pressure is inversely proportional to the volume. So the pressure is, I think they use K over V, and we sort of need to find the K, so we know that pressure of 500 pounds per cubic inch, per square inch, I'm sorry, is equal to K over 2 cubic feet. All right, so K would then be equal to 1,000. Don't tell me they messed it up like that. No, I'm sorry, I misread it. The pressure is in pounds per square foot. Thank you so much. Okay, if that was per square inch, we got a big problem on our hand. Per square foot. 500 pounds per square foot. Then that would be, K would be 1,000 pounds per foot. No, foot-pounds. Yeah, 1,000 foot-pounds. That seems so bizarre that that would be your unit there, but that is what it turns out being. They don't pay attention to units, but now they got K is equal. I've done so. Oh, no, sorry. The delta V here, it changed from 1 cubic foot to 2, so that was just a 1 cubic foot change. So that left us just 500. Sorry, I was putting the final, not the change. The change is 500, and that would be foot-pounds. They don't ever put the units there, but that's what it comes out being. So your work, from what we had before, the work is equal to, if you recall that, the integral of your K, which was 500, happens to be foot-pounds, and it's going from 1 to 2 cubic feet, and it would be dV over V. Okay? I believe that's it. I put the K out front, they left it in. So this would be what? 500 times, what is the antiderivative of dV over V? Second? Antiderivative of dV over V? 1 over x dx. Antiderivative of that? No, that's going the other way. power rule doesn't work here because this would be V to the minus 1 at a, you would get over V to over 0. This doesn't work. What's that? Antiderivative of 1 over x dx. Second? The log of x, exactly. So it's 500 times the log of v, natural log of v, okay? And that's going from 1 cubic foot to 2 cubic feet, okay? So this will be 500, and you tell me what log, well, it's just going to be log of 2, and you tell me what log of 1 is. 0, okay, so there's your answer there. And if someone has a calculator, log of 2 times 500, the book has approximately what you get.
346.
That's what they got. 346.6, and they have it as foot-pounds. Now, I can't quite rationalize in my head how they come up with the units. They just do it at the very end. But they don't carry it through all the way. They just throw it in. Those are the units. So rather than mess with it too long, we'll just take their word for it. All right. Any questions on that? These are sort of, again, well, in this case it gave you a little more problem. Setting up the problem is the problem. The integration, once you recognize that's a log function, that's a piece of cake. So the calculus part's the easy part. Setting up the problem, though, is the part that requires a little more effort. Sorry I messed this up because when you do this, this is the change of value here, not the dividing. It wasn't 2, it was 2 minus 1 is 1. So that's why it takes 500 rather than 1,000. Okay, homework exercises, either 5 or 7 or both. They're both at Calc Chat. 7's at Calc View. Any of the odds 9 through 13, they're all at Calc Chat. 11's at Calc View. 15 or 17 are both propulsion problems. They're both at Calc Chat. Pumping water would be either 19, 21, 23, 25. So I'd say any of the odds 19 to 25, pumping water problems. 27's a pumping gasoline problem. Either 29 or 31. They're both at Calc Chat. 29's at Calc View. 33's moving a chain problem, like we just did earlier. That should be at Calc Chat. There's an exploring, think about it type problem. You can think about doing 35 if you'd like. And then there's a problem on Newton's law of universal gravitation or electric force. Or ordering forces, if you want to order some forces for supper or something. That's any of the odds 37 to 41. Okay, Boyle's law 43 is at Calc Chat and Calc View. Hydraulic press problems 45 and or 47, both at Calc Chat. 49 is a modeling problem, and then they have the pyramidal Khufu, or however you say that. You can look at that if you're interested. All right, any questions on 7.5? And let's move on to, so work was another application of integration. Let's move to our next application, which is a very long section here, or lots of slides anyway. So it's going to take a little longer to open. There we go. Okay. I'm having trouble seeing. There we go. All right, just finished, we did the launch, and earlier in the last section before last, we just did the pyramid and the end of that one. So let's move on to moments, center of mass, and centroids. Now, some books really string this out. This book does a fairly good job of streamlining this and making a bit more reasonable. I've seen some books that just can drag this on and come up with all sorts of weird examples. This keeps it pretty straightforward, I think, if my memory's right. So our objectives here are to understand the definition of mass. That's pretty vague, isn't it? Find the center of mass of a one-dimensional system. Find the center of mass of a two-dimensional system. Find the center of mass of a planar lamina, which basically is a two-dimensional sheet of something with uniform density. So that's what they mean by planar lamina. And we'll use the theorem of Pappus to find volumes of solids of revolution. They love those, don't they? All right, so let's start with mass. What in the world is mass? Several important applications of integration are related to mass. Mass is a measure of a body's resistance to changes in motion, which you could say inertia. Mass is related to inertia. The body's resistance to change in motion pretty much defines inertia. Independent of the particular gravitational system in which the body is located. And that example with the rocket going up, and they were using a mass unit to measure a force and just doing all sorts of weird things with that. Your force was varying as you're going up because they were doing force. Mass doesn't vary. No matter where you are, the mass is the mass is the mass. Now, why did that happen? I wasn't anywhere close to it. That seems to be, there we go. There we go. Okay. Independent of gravitational system or anything else, it's just how much material is in the body. However, because so many applications involving mass occur on Earth's surface, the object's mass is sometimes equated with its weight. I can't be pressing on the wall that much because that not the same problem as before. I know when I mess with this, it's going to fiddle with the other problem, but let me try it. I say they're not related. Well, the fact that this box wiggles and jiggles like this is enough to scare me, but I don't know what's happening here. Anyone got a sledgehammer? Yeah, let's get it so it'll listen to us here. Okay. I've tried tightening. Let's see what loosening will do. That doesn't do anything beneficial. There we go. Of course, as soon as I say it doesn't do anything, it does something. Can I explain? Okay. I hope this is the next slide and it didn't advance or something. I think it is. So that. Oh, this is what we're working because so many applications involve object's mass is sometimes equated with its weight. I hate statements like that. It's not equated with, is related to its weight. Okay? The mass is related to the weight. It's not technically correct, which is absolutely true. Weight is a type of a force, and as such is dependent on gravity. Force and mass are related by the equation. Force is equal to mass times acceleration. On the surface of the Earth, this acceleration is usually g, acceleration due to gravity, and that relates mass and force. Now, I don't know if they're going to get at that or not. No. The table below is some of the commonly used measures of mass and force together with the conversion factors. And in reality, in the U.S. system, have you ever used a mass unit? Have you ever gone to buy a slug of potatoes? They wouldn't know what you were talking about. Nobody uses this, okay? Now, a kilogram is a kg, a gram's a g. Slug doesn't even have an abbreviation. No one uses it. They don't even bother to abbreviate it. If you ever use it, you have to spell it out. S-L-U-G. Usually it's not capitalized, neither a kilogram nor gram. Okay, measures of force, much more common, and those are just pounds. Okay? Now, technically a pound is a slug force per second squared, a mass times an acceleration. In the SI unit, that's System International, SI, is kilogram is the measure of mass, and a newton is a kilogram meter per second squared. Because meter is the SI measure for length. Foot is that U.S. customary measure for length, standard. So this is how these relate. Now in CGS, that hardly anyone uses anymore, and this book loves to talk about it. Gram is the measure of mass, and the dyne is a gram centimeter per second squared. Mass times acceleration, that would be the measure of force. With some conversions down here, they use this in that last problem at the end of it. See, you relate pounds and newtons, and a pound is much heavier than a newton. 4 times heavier, 4.5 to almost times heavier than a newton. So a pound is the bigger unit, so it takes more newtons to make a pound. A newton is just a fraction of a pound, between a fifth and a fourth of a pound. And then dyne, people hardly use this. These are approximate because they're not exact. This is exact because this is within the same units, metric units. So that's what that is. Slug, oh goodness gracious, is a pretty massive quantity. Okay, more than 14.5 kilograms, and a kilogram is really massive. Okay, so this is a pretty big, massive unit. And a kilogram is less than 7/10 of a slug, 7/100 of a slug. A gram is in a tiny little bit, and of course a foot and meters are related by that. I would not worry about any of these. Usually you can look them up if you ever need them. But this is so unusual, I didn't know it was that many kilograms. I've been working with these things all, because no one ever uses slugs. Okay. So here's example 1. Don't think there's much calculus involved with this. Find the mass in slugs of an object whose weight at sea level is 1 pound. Okay? So how do we relate the mass to weight? Okay, mass, well, let's do it the other way. Weight is equal to mass times the acceleration, and we're going to use g. Okay, so we're looking for mass, so let's divide both sides by g. G whiz, okay? So mass is equal to weight per unit acceleration of gravity, which this is 1 pound divided by 32 feet per second squared. Well, what's a pound? It's a slug foot per second squared. So divide out the feet per second squared. And what do you have? 1 divided by 32. That's some fraction we should all know, but I don't recall it right off the top. 1.00. No, just 1 0. 0.3125, is that it? 3125. Slugs. Again, I said slug is a very big unit, so a pound, which is, not that heavy, but that's just an incredibly small fraction of a slug. So a slug is proportionally quite a few pounds. Okay, because many applications involving mass occur on the Earth's surface, this amounts to what we call a pound mass. That is what we call a pound mass. That's why no one uses slugs. If they refer to something, they'll say a pound mass, which pounds measures weight, but you're using the mass equivalent of that 1 pound. Now, why they go into that, I'm not certain, because I'm not sure they use it anywhere else. Maybe it'll come up at some point, but it's not necessarily. Okay, so let me clear this out of the way. I've sort of been carried away in my own world here and haven't noticed when people have been leaving. How are we doing time-wise? See, we started at 11:30, right? So if we need to, in a little bit, we'll take a break. Give me about 15, 20 minutes. Sound reasonable? Okay. I think that's about halfway through the class, right? I think that's right. Okay. All right. So let's see how they did it. Using 32 feet per second as acceleration due to gravity, mass is equal force divided by acceleration. That'd be 1 pound divided by that, which is 0.03125 pounds per foot per second, which is slugs. Because many applications, blah, blah, yeah, okay, we already said that. All right, center of mass in a one-dimensional system. That means you're just going along a line here and talking about a center of mass. We'll now consider two types of motion. Two types of moments of the mass. The moment about a point and the moment about a line. Okay. Have any of you had your statics yet? Okay, they're in the future. Okay, you'll be dealing with this kind of stuff, I think, a whole lot in statics. I never took statics. I was a physics major, not an engineer, but I've tutored enough and stuff. My memory a while back seems like this is statics. I believe this is dynamics. Maybe you'll get into it in dynamics as well. To define these two moments, consider an idealized situation about which a mass is concentrated at one point, not a blob, but just a point. That's a very common assumption or construct. If x is the distance between that point where all that mass is located, that point mass, and another point p, then the moment of that mass m about that point p, here's the mass here, here's the point p, the moment is the product of the mass times the distance between those 2 points. If x is the distance between them. And x is also called the length of the moment arm. I know that sounds like a static type phrase to me. I think it is what the common nomenclature for it. So the concept of moment can be demonstrated simply by a seesaw. Okay? A child of mass 20 kilograms, sits 2 meters to the left of the fulcrum P. Okay, and the older child of mass 30 kilograms sits 2 meters to the right of point P. Where's that going to go? Yeah. This kid's going to go down, the other's going to be up there and screaming, "Get me down!" Okay, or something like that. Okay. From experience, you know that the seesaw will begin to rotate clockwise, moving the larger child down and the smaller child up. because there's a greater moment. This child has a greater moment, same distance, greater mass than this child, same distance but lesser mass. So a greater moment is going to create the movement. Seesaw will balance when the left and right moments are equal. Okay. This was always, in my case, I was always the heaviest kid in the class. I never could seesaw with any of those. I have to sit way up here, something like that. Okay. This rotation occurs because the moment produced by the child on the left is less than the moment produced by the child on the right. 40 kilogram meters, the left moment, 60 kilogram meters, the right moment. To balance the seesaw, the two moments must be equal. For example, if the larger child moved to a position 4/3 of a meter from the fulcrum rather than 2 meters, 1 2/3, then 1 1/3, then the seesaw would balance because each child would produce a moment of 40 kilogram meters. So if you multiply rather than by 2 by 4/3, 4 over 3, 3 will go into this 10 times 4 is 40. So that's the same thing. Then they'd be even. Okay. You can introduce a coordinate line on which the origin corresponds to the fulcrum, is shown here, and several point masses are located on the x-axis. The measure of the tendency of this system to rotate about the origin is its moment about the origin, about a point. And it's defined as the sum of the end products m sub I times x sub I. So if this looks like a negative x over here and some mass here, now notice they didn't give that, so let me back off from that. No, I think you really do need that. Make that a negative x and this mass, negative x of 2 here, times that mass. Positive x of 3 times that mass, usually. It's coming. You keep adding these masses, right, left, wherever. M sub n minus 1 times x sub n minus 1, m sub n times x sub n. These are all the masses. And if the sum of all these masses is 0, then the system is in equilibrium. So you see, some of these x's would have to be negative, some of them would have to be positive in order to ever have a chance of being 0. Before they said 40, 60, they balanced it, this and so. But one of them had to be a minus, one had to be a plus. And that's why the kids went down, because the plus was greater. All right, so this is a setup for the moment about a point, specifically the origin. The moment about the origin is denoted by m sub 0 and can be written as m1 x1 plus m2 x2 plus m3 all the way up to mn xn. Understanding some of these x's could be positive, some negative. Okay? If m sub 0 is 0, then the system is said to be in equilibrium. That would be your static case, and that would be some of these x's certainly would have to be, at least one would have to be negative, and probably more than one negative, so positive, and then you would have your moment to be 0, meaning it's in equilibrium. For a system that is not in equilibrium, now I don't know if this is where dynamics comes in, but the center of mass is defined as the point x bar at which the fulcrum can be relocated to attain equilibrium. If the system were translated x bar units, and they could be to the left, negative, or to the right, positive, then each coordinate x of I would then be x of I minus x bar, because you're that far from the equilibrium position, some to the left, some to the right. And because the moment of the translated system is 0, you have that the summation from I to n, I equal 1 to n, would be m sub I times your x of I minus x bar. Now this x bar, remember, is fixed, so x of I minus this will sometimes be positive, sometimes negative. Okay? Now, what you can do with that is distribute the m across both of those, and this is your summation for I to equal 1 to n of m sub I x of I, which is just from what we said before. Basically m sub 0. That was your summation of all those. Okay? Minus your summation x of I 1 to n m sub I times x bar, where x bar is some fixed position, so this is just going to be a fixed amount. And that would be, if now you place this, so this x bar is your center of mass, then this has got to be 0. Right now you can balance that. And now, I wasn't paying attention. Sorry about this. That last jiggling I did, this waited till the third class last week. Well, it flashes in and flashes out. It comes on sometimes when I'm holding it, sometimes when I'm not, but it won't stay on now. I'd been doing such a good job of keeping my eye on it until I didn't. I think they're ordering me a new laptop, but it's going to be a while, so I'm trying to make this one last, because they don't have many of them that have the ionizing pins. Get back on. It's okay. Nope. You see every now and then it does a little blink. My screen is blinking. Now I can't tell, because when I look at this, I can't see that one too. It seems to be, this is how it was the third class last Wednesday, the whole way through, just fluctuating. It seems to be sort of stable now, so let's hope it works. Okay, so if you moved your to the center of mass, then this thing will be equilibrium, and that's going to be 0. Well, this x bar is what we're going to try to locate now. Okay, your center of mass. So what you can do is move this to this side of the equation, and then divide by this. Well, what do we have then? We have the summation from 1 to x equal 1 to n of your x equal 1 to n, your m sub I x sub I, which is the moment of the system about the origin, which we had before. Now I went back and flicked on that. Yeah, it still seems to be holding steady. Divided by your total mass. The summation of all your little masses from I to n, that's your total mass of the system. So there's your definition for your center of mass. Okay? And when all these, which is this numerator here, adds a 0, the center of the mass, the system is equilibrium, your center of mass is that origin. Okay? So there's your, the equation we'll be using for finding center of mass. Okay. I almost hate to touch it, afraid it'll knock it out, but okay. So, one-dimensional system, meaning we're talking about a seesaw here, a single line, all the masses on the line. Let the point masses m1 and 2 all the way up to m sub n be located at x1, x2, x3, x4, wherever they are, all the way up to x sub n. And the moment about the origin is your summation of all these, m sub 1, x1, m sub 2, x2, all these, about the origin now, okay? And the center of mass of the system will be that moment about the origin divided by the total mass of the system. Total mass of the system, all these m is m1 plus all the m added together. That's the center of mass. Fairly straightforward, not that hard to usually compute thing if you have a finite number of masses, okay? As long as that finite number isn't too big, okay? Now, here's our example 2. That seems awfully stable. This doesn't. This is just flickering like crazy. Okay. Find the center of mass of the linear system shown in this figure here. Okay? So here we've got your scale here arbitrarily is 0 there. And what would be the center of mass? What symbol do we use to represent it? X bar. And how do we define it? The sum, okay, your moment, m sub 0 over the total mass. Okay? Now your moment, remember what that is? Just the coordinate times the mass, x or m times the coordinate. That would be, now they don't give any units here, so we won't have any units. It would be 10 times minus 5, which is negative 50, plus, and what does that next one give you? 0. 15 times 0 is 0, plus 20, plus 70, is that what I heard? Divided by what? $40. Very good. Even that one that's at 0, you should count it because that's part of the mass. Okay? So you got 10 and 15, 25, 30, 40. Okay? So what does this add up to? 90 minus 50 is 40 over 40, which is 1. So there's your center of mass right there at x equal 1. Okay? Make sense? All right. Now let's see if indeed that's true. How far is this 10 from the 1? 6. 6 times 10 is, this is minus 6, so minus 60, that's 1 away, so minus 15, that's minus 75, right? Okay, how about this one? How far is that away? 3 times 5 is 15. This is how far away? 6 times 10. 60 plus 15, 75 to the right, 75 to the left. Perfect. Okay? So, yep, that is your center of mass of the system, x equal 1. Okay? So, oh, there it is. Okay. That was equal to 1. Now, let's see how they do it. Let me clear my scratch out of the way. The moment about the origin is the sum of all the moments. M1x1 plus M2x2, all that. That comes up to be 40. Okay? And that would be in mass distance measures. They don't give us any here, so that'd be kilogram meters or whatever. Okay? Because the total mass of the system is, just add those four together, that's 40. Then your center of mass is your 40 kilogram meters divided by 40 kilograms, and that would give you 1 meter or 1 centimeter, whatever your units were. Okay, your x bar would be one length unit away from the origin in the positive direction. Notice that the point masses will be in equilibrium when the fulcrum is located at x equal 1, and we just did that. Okay, rather than defining, I feel paranoid now. Rather than defining the moment of mass, you could define a moment of a force. In this context, the center of mass is called the center of gravity. Consider a system of point masses, M1 up to Mn, located at the positions x1 to xn. Then, because the force is mass times acceleration, the total force on the system is F is equal to M1 A plus M2 A plus M3 A. But notice here it's a whole system. So if the system has an acceleration, it's the same throughout, because we're assuming a rigid body system that everything moves along. So the A's are all the same, so it's the sum of all the forces, sum of all the masses times the acceleration of that body. Okay. The torque, or the moment about the origin, and this is a rather unusual symbol for torque. Most of the time it's a tau. And I've seen it little tau and capital tau. I don't know if y'all had anything with torque yet. What do you use, capital tau or little? Huh? Okay, that's what I've always seen too. So the little tau, they call it capital T0, is your force 1 by displacement 1, force 2 by displacement 2, all the way up, force n on displacement n, and then that would be your tau. Boy, what a weird. Okay. This is that, your system moment, okay, times acceleration over your total mass times acceleration, which, guess what? Does that look sort of familiar? Same way we defined it before. So the ratio of torque to force also gives you your center of mass. I was wondering what they were, which way they were going. Called the center of gravity, but it's exactly the same measure. Okay? So the center of gravity and the center of mass have the same location. Now, where one use of this is, and this example I'm going to give is going to be sort of three-dimensional, but you can extend it to one. So let me try to make it one-dimensional. If you had, say, a rod here, just assume that's uniform density and stuff like this. If you had the center of mass, you would know where to attach something and pick it up, and it would go up flat. If you go either side of it, it's going to tilt, and you're probably going to fall off. Extend that to two dimensions anyway. And I can remember hearing about this. I never actually saw it. When I was in probably elementary or junior high school, some fairly recent Olympics before that, the heavyweight weightlifter winner of the gold medal for that Olympics lived just down the road in the next town south of my hometown. His name was Paul Anderson. He, I think, set a record that Olympics. And he was a motivational speaker, too. I don't think his speaking was all that much, but everybody paid attention to him because he was an Olympic gold medalist in weightlifting. And what he would sometimes go and teach the younger grades, talk to younger grades, and he would have them sit on the platform, and he would go under the platform and lift the entire class, on his shoulders. He was one strong dude. And, but his point being that he had to know the center of mass, otherwise he could dump them all. because if he was anywhere off of that center of mass, they're going to tilt and they'd be all falling over. Now, I don't know how he did it. He never did it at our school that I knew of, but supposedly that was one of the things, and it made a profound impression. And he talked, extended that on finding your center, and he did something pretty nice with it. But anyway, that's exactly what we're talking about here. That's a two-dimensional example. If you found that center of gravity or center of mass, then you have it. Now, that then lends itself to, in other contexts, when you're talking about multi-body systems, you don't have to represent every body as a finite body. You just locate the center of masses and deal with the center of masses, and it's a lot easier problem to deal with. So it's going back to sort of running full circle with that concept. So let's move to center of mass of a two-dimensional system, which is what I was just describing. You can extend that concept of moment to two dimensions by considering a system of masses located in xy plane at various points, x1, y1, x2, y2, x3, y3, and so on, and having each mass at that point be m1, m2, m3, and mn, all of them, okay? Rather than defining a single moment with respect to the origin, the two moments are defined, one with respect to the x-axis and one with respect to the y-axis. Now, this is the place where it gets maybe a little confusing, is remembering this. The moment with respect to the x-axis is going to be your y bar, because that's going to be a y measurement, okay? And the moment with respect to the y-axis is going to be your x bar. So if a two-dimensional system, there's a moment about the y-axis, and that moment is m sub y, where before it was about the origin, m sub 0, and the moment about the x-axis is m sub x, but this is a y measurement, that's an x measurement. Don't let the subscripts throw you around there, okay? So here's the definition. Let the point masses m1 through mn be located at the ordered pairs x1, y1, x2, y2, x3, y3, up to xn, yn. Each one of the subscripts matching the masses matching the subscripts of your points. The moment about the y-axis, m sub y, are your x's here, not the y's. M sub 1, x1 plus m sub 2, x2, sub m sub 3, up to m sub n, x sub n. Moment about the x-axis, m sub x, capital M sub x. Moment with respect to the x-axis is your little m1, y1, little m2, y2, little m3. Those are your masses times the displacement from the x-axis, which is measured on the y-axis, okay? So the center of mass, now x bar and y bar, or center of gravity, if you want to call it that, is for the x bar, because these have the x's in them, this is your m sub y over m, and your y bar is m sub x over m. Remember, the moment about the y-axis measured in x units, and moment about the x-axis is measured how many units above or below it. So those would be y units. Now, this m down here is the sum of all your masses. Now, in many books I've taught for, they call this capital M. So now it looks a little better. You don't get them confused here, but this book uses little m there. So if I ever put capital M, that's just because I'm going to another book. So the total mass of the system. Make sense? Maybe better if we do one, but let's do a little bit more. The moment of a system masses in the plane can be taken about any horizontal line or vertical line. You don't have to use it about an axis, the x or y axis. In general, the moment about the line is the sum of the products of the masses and their directed distances from the point to the lines. Now, what do we mean by directed distances? Basically, perpendicular distances. If you got a line like this, the moment's about that line, the perpendicular distance from that line. Okay. We're not going to be doing that much about this, but so we're going to assume that these lines that they're about, this will be a lot easier, are horizontal lines and vertical lines. Horizontal line would be y is equal to b, and vertical lines will be x equal a. So these would be lines like this. Your mass times how far that y is from the original yb. Now this could be a positive or a negative quantity, depending on whether y1 is the left of b or right of b. This could be positive or negative, but each of these could be. And that would be your moment about that line y is equal to b, and this would be the moment about the line y is equal to x equal a. And again, this is the vertical line x equal a, wherever that happens to be, these will either be positive or negative. So, don't think we're going to be doing much with that. Let's do example 3 now, with regular axis. Yeah. Find the center of mass of a system of point masses. M1 is 6, M2 is 3, M1 is 6, M2 is 3, M3 is 2, and M4 is 9. So the size of the circles is relatively speaking the masses. Smaller circles 2, 3, 6, and 9. Okay. Located at M1 is at 3, M1. There it is, okay. 3, negative 2. M2 is at origin 0, 0. M3 is negative 5, 3. And M4 is 4, 2. Okay? So what we want to find is the center of mass of that system. Okay? You tell me how you would start. All right, if we start with X bar, what would that be? Okay. You're going to start with M1? What, is that what you were saying?
Or, yeah, so it would be like, yeah, so like mass 1, x1 plus.
Yeah. 6 times 3, is that what you're saying? Yeah. 6 times 3, that would be 18, plus, anybody contribute to the second one? 0, okay, yeah, 3 times 0 is 0, okay, plus the next one, second, negative 10, so that'll be a minus 10, plus what? 30, what'd you say? 36? Okay, I can't hear well. I kept hearing a 32, I thought. How do you get that? Okay, no. Plus 36, okay? Divided by? A little louder? Okay. The total masses are, yeah, 20. All right, 15 plus 5, yeah. Now, what does that add to? The positives go to 54 minus 10 is 44. Is that right? Over 20. And this will be 2 point what? 2.2. 2.2. Okay. So that would be somewhere about there. Okay? But not necessarily on the x-axis, somewhere about there. Does that seem reasonable? Boy, these are pretty far away from that. I mean, already they're concentrated here. We see most of the mass is concentrated here. This one doesn't contribute much to the center of mass. So yeah, that's a long way off there. Okay? How about the y bars? Negative 12. Plus 0. Plus what? Did I hear? I can't hear. 6 plus 6, okay. Plus 18, okay. All divided by same total mass, 20. Okay. Now this, if I'm not mistaken, is 12, is that right? 12 over 20, which would be 0.6. Something about right there, maybe? So there would be my center of mass. If I can get it to draw there, something like that. Okay. That's the center of mass. And again, this big one has pulled lots of things toward it. Okay. Staying close, certainly these two have pulled everything out this way. But this is not very big mass, and this is a decent size, it's fairly small, so that does look, pretty reasonable. So again, the big heavy kid over here, okay, and then the lighter one out here, way out there, not contributing very much. So that's where the guy would get underneath the platform to pick up those 4 kids.
What is that one there?
I'm sorry?
Is that the one there, X bar, Y bar?
Yeah, then this is the X bar, Y bar, that's the center of mass. I tried to draw it somewhere in there. My pen kept blinking on and off, so I wasn't somewhere around those 2 hot dots. The other, I couldn't get it to, I couldn't see where it was drawing, and I kept trying to get it to happen, and then 2 of them showed up, the rest of them didn't. And they should have been the same one. Yeah, that's your X bar, Y bar. Yeah, that's your center of mass of that system. Let's see what they got. Oh man, yeah. They kept it in fraction form, 11/5, which is 2.2 and 0.6, which is 3/5. Good deal. Okay. Oh, I forgot they showed the answer too. So they identify the 4 masses, total of 20, and they started with M. The moment with respect to the y-axis, which is going to produce your x bar. 6 times 3, the first one, plus 3 times 0, plus 2 times -5. That's the x, plus 9 times 4. That came out 44. And m sub x, which is the moment about the x-axis, which is going to be your y value, will be 6 times, the y value is 6 times -2, plus 3 times 0, plus 2 times 3, plus 9 times 2. And that gave you 12. And then when you divide them, 44/20 is 11/5, or 2.2, and the y bar is your 12/20, which is 3/5. So it's 11/20, 3/5, or 2.2 over 0.6, or comma 0.6. Okay, and amazingly, that's where they stop in the slideshow. Oh no, that's all they do in the book too. So let's do the center of mass of a planar lamina. And how are we doing on time? Still got an hour to go, right? Yeah, okay. Center of mass of a planar lamina. I keep having trouble saying that. Consider a thin, flat plate of material of constant density called a planar lamina. Okay? Now, density is the measure of mass per unit volume, such as grams per cubic centimeter. In planar laminas, however, because the density is of a plane, is usually a measure of mass per unit area, because you're assuming the plane is uniform thickness. Okay? So, we'll use mass per unit area. Bit different from what you normally think. Density is usually denoted by rho, which is lowercase Greek letter, okay? Now, they say that. In some texts, they only use rho if it's mass per unit volume. They use, I can just remember, they have a link one and also an aerial one. Can't remember, I just had it on the tip of my tongue and now I've lost it. But they sometimes will use different symbols, but this book uses the same. So they're going to use rho for density per unit volume or density per unit area. I don't know if they're going to do it per unit length, but I would imagine they would. So you can think of this center of mass of the lamina as its balancing point, which is what I was saying before under that platform. If you got under the center of gravity, then you could lift the whole thing without tilting it. For a circular lamina, the center of mass is certainly the center of the circle. Rectangular lamina, the center of mass is the center of the rectangle, which is the cross-section of the two colors. I don't know if my mind's going completely blank. The bisecting lines, what? It's gone completely blank. But that's the center of the rectangular one. Obviously, but even if that were a parallelogram, same type deal. Okay. Really, an odd-shaped figure, no, you can't do it. But anything that's fairly regular would work. Okay, consider an irregularly shaped planar lamina of uniform density. Now that's the key. The density of this is uniform. So what we're ultimately going to do is count that as 1. Since it's going to fall out of everything, we'll count as 1. But for now, our development of it, will let it be rho, whatever that is. Bounded by the graphs of y is equal to f of x up here, and y is equal to g of x down here. Don't even have to be close to the same shapes or forms or anything just now. The a certainly less than b, but your x's are always going to be something between a and b. So a is less than x, and x is less than b. Less than or equal. It can be right up to the end. Shown here. The mass of this region will be the density of the whole region times the area. The density is fixed. It's a uniform density. That's what we're saying. So density times the entire area of that. Well, we know how to calculate areas. It's the integral between the length of these little rectangles, f minus g, times the width, which is your dx. So f of x minus g of x dx. That's rho times the area, where A is the area that we use in integration, application of integration, to calculate that. Now, that's if the f and g are functions of x. If they were functions of y, you just do the same thing with that. To find the center of mass of that lamina, partition the interval from A to B into n subintervals, boy, the same deal as always before. N subintervals equal with delta x. Let your x of I be the center of the ith subinterval, okay, which they had a picture here. Yeah, there it is. X of I is the center of that subinterval, and your y sub I is going to be, because this is uniform, the center of that rectangle, which is halfway between these two, halfway between those two, that is the center of the rectangle. That's your x of I, y sub I. The center of that strip, which is the center of mass of this strip too, by the way. Okay? X of I be the center of the ith subinterval. You can approximate the portion of the lamina lying in the ith subinterval by a rectangle whose height is h, which is f of x of I minus g of x of I. and because the densities of a rectangle rho, the density of the rectangle is rho, and that's uniform, that's constant, then its mass is m sub I of that ith strip is its density times its area. Its density is rho, we know that, and the area is the length times the width. Okay, alpha minus g times dw, delta w or delta x here. Okay. Now, considering that mass to be located at the center of mass, x sub I, y sub I of the rectangle, the directed distance from the x-axis to x sub I, y sub I would be y sub I from the x-axis to be the average of those two. Okay? The average of the two. Now let's go back to the picture. Now, even if this thing were down here, or all down here, or wherever it was, okay, the sum of these two divided by 2, that's the average. Whether it's here, 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 wherever it is, the sum of those two divided by 2 is going to be the average. Okay? So that's going to be key. Now that's because it's uniform density. If that was varying density, you can't say that. Uniform density, you can. Okay? So the y sub I for the directed distance from the x-axis is y sub I, which is the average between these two f and g of x sub I divided by 2. Sum divided by 2. So that the moment m sub I about the x-axis would be its mass times its distance, and that would be m sub I times y sub I. M is the mass, and the distance above the x-axis is your y sub I. This thing right here. So, backing up, this is the height, there's the density, the height, the width, and the position of your center of mass. Okay? L sub I G, G of I over 2. Okay? Now, the interesting thing that this gives you is, here's the difference times the sum of the same two numbers, the conjugates of each other. And we know what they, when you multiply them together, give you what? Alpha of I squared minus G of I squared. A minus B times A plus B is A squared minus B squared, right? So it's the same thing here. So that's making this then a pretty simple case. Well, no, it isn't. Okay. They just sort of skip right on to that. The f and g be continuous functions, so the f and g, this is going back to the moments, okay? F of g is always greater than or equal to g of it. F of x is always greater than or equal to g of x on the interval a to b, and consider the planar lamina of uniform density rho bounded by the graphs. The top is y is f of x, bottom y is g of x, left is a, right is b. The moments about the x and the y axis are, now these are your moments, okay? M sub x is your rho, okay? That's just density, okay? And that's mass per unit volume, unit area, because we're dealing in an area. Okay, here is the height, there is the this is the average, M, there's the height, and there's the thickness, okay? So it's, where is this located? In times this is mass per unit area. These two together give you the area, the length times the width, and this is how far it's located from the y-axis. Okay, so that's that. Now, m sub y, this is from the x-axis. That's just your rho times this is your, again, this times this is your area. This is mass per unit area. So this is the area, and this is your location from the y-axis, m sub y. That's just your x. See up here, you want this in terms of x, so you can't just say y. This is your y, okay? But you need it in terms of x, so that's the average of your x's. So the center of mass, x bar, y bar, is given by x bar is this m sub y over m. The y bar is the m sub x over m. And then the m is the density times the area. Length times width, that's the area. That's the mass of the line. So this is usually the first integral you do to get the total mass, because you use that in both of the others. So here's example 4, where we put all this together, and hopefully it makes some sense. Find the center of mass of the lamina of uniform density, rho, bounded by the graph 4 minus x squared and the x-axis. Okay, now let's get this on here. Okay. When x is equal to plus 2 or minus 2, this thing is equal to 0, right? So, and you're bounded by the x-axis, so it's all going to be above that, okay? And when x is equal to 0, this is up here at 1, 2, 3, 4, right here. So here is your, boy, that's an ugly parabola, isn't it? It's a parabola that looks something like that, okay? Somewhere in there. Okay, and you want the center of mass of that. Since it's uniform density, no variation in density here, can anyone tell me what x bar is going to be? 0, because this is uniform density and it's symmetric about the y-axis, the x bar is going to be 0. So really all you have to figure out is y bar, okay? Now let's back up a moment and let's make some guesses. You think it's going to be closer to 1, 2, 3, 4, 0. Which is it going to be closer to? 1. I tend to agree with you, okay? Because you see you have less mass up here, much more mass down here because it's uniform density. So it's going to be down from, it's not going to be midway, okay? Midway this way, x bar is equal to 0, but your y bar, we're going to have some more calculating to do. So, all we have to do, we know the x bar is equal to 0 by symmetry. So let's do the y bar. Now what's one thing you've got to get first, probably? Let's just picture our little rectangles here. Okay, this is a delta x. And the height here is your what?
Specific rectangle or a whole thing?
Any old rectangle there.
2.
Second?
2.
I can't hear.
2.
2? Well, no, this is above 2. I'm not saying, okay. Yeah. This is going to be your y value, but what's your y? F of x. So that's going to be your f of x. That's the height of it. The width of it, of course, is your delta x or dx. So you're going to sum all those now. Here comes another little dilemma. Can you just do 0 to 2 and double it. This is the distance from the y-axis is what we're doing here.
I guess since it's uniform density.
Pardon me?
I think you can because it's uniform density. So you should
Yeah, it's uniform density, everything's the same, but yeah, I would think the y bar is going to be the same way you just did. Let's just do the whole thing just for safety's sake, okay? So, your y bar is going to be your, think of this, they like to do m sub x's and that kind of stuff. I tend to want to go your distance, which is going to be your the average between these two, and since the bottom one is always 0, the g of x in this problem is always 0. This is going to be f of x over 2, okay? That's the distance up here, times the length, which is f of x, times your dx, which is your width. That's going to be the fractional, so you're integrating this 0 to 4. Right, I'm sorry, 0 to 2. Remember what we said, let's go negative 2 to 2. Because you're doing dx's here. So we'll go negative 2 to 2, and this length of this is f of x, and the position of it is f of x over 2. Distance from...
Doesn't that integration give you 0?
Second?
You can go from a negative number to that same number but positive. Isn't that integration 0?
If we were doing the x bar, yeah, that's why it comes up here. Okay? But we're doing the y bar, and its distance is this. So this is a positive value, that's a positive value, that everything's positive, so I don't think it can possibly come out 0. Okay? But we'll see. Let's take a look and see. Okay? So it looks like to me this is going to be, this thing flashing on me just drives me nuts. You don't see it there. Every time I look at the screen, it's almost enough strobing to give you a headache. Okay? Integral from minus 2 to 2 of your, this thing squared, so it's 4 minus x squared dx. Now let me, before I go too far with this, just make sure yeah, okay. Now, I'm saying y bar always has with it divided by the total mass. So we've got to do that as well. Okay. So maybe we should have done that first. Let's do that. Let's get what the mass is. What is the mass then? Now this I know you can double. Without a doubt, I know you can double this one. This is 0 to 2, twice 0 to 2. Between the strobing and my cataract, this is really driving me nuts here. But you have the 1/2, wait, yeah. No, this part was just your distance above, so here you have your f of x, the height times the width, d of x. So this 4 minus x squared dx. Okay, and we're going to double that. So what does this give you? 2 antiderivative of 4 minus x squared. 4x minus x cubed over 3, evaluated from 0 to 2. So So this will be 2 times help me somebody. 8 8/3. Okay, the zeros don't contribute anything, and this is 0 to 2. So this is actually 2/3 of 8. So you've got 2 times 8 times 2/3. Is that, and this is evaluated from 0 to 2. Sorry. Okay. So that would be 32/3. How have I left off my x's? Oh, no, I'm sorry. Yeah, I think I'm okay. I think it's 32/3. Okay. Yeah, there it is. Oh, I'm sorry. Remember, we had our rows in here. I forgot to put the rows in there. Okay. But you see, as you'll see, 32/3 row. Okay. So that's the mass. Okay. Over here, you got the rows in there too. And guess what? The rows will wind up canceling out. So that's why I forget about my rows, because they're in the one side, they're in the other side, they divide out, so they disappeared. So I'm going to leave them out so I don't have to carry them around any further. So now we've got to square that, okay? And I hope I've got my, yeah. All right, so this is going to be 1/2. I'm going to leave the rows out. Let's square that first. The integral from -2 to 2. Square that. Anybody? 16 minus 8x squared plus x to the 4th, and that's going to be dx. And that's going to be over 32/3. Okay. I'm rapidly running out of room here. That was fairly alliterative, wasn't it? Okay. This will be 1/2 of, what's the antiderivative of 16? 16x minus 8x cubed over 3 plus x to the 5th over 5. It's evaluated from, let's see, -2 to 2. And this is all over 32/3. Don't let me forget that one. And let's evaluate that numerator. All right. 16 times 2 is 32 minus 64/3 plus, I think that's 32/5, isn't it? Okay. That plugging into 2. Now let's do the -2. That would be a -32. Those go out. But then you have second. That's what I was just looking at. I'm afraid it is. No, wait, okay. You know what? These minus signs are there for to trip you up. Okay? You have a minus this one was fine because it's just this minus this. Okay. This one you have a minus, which is a plus, but then you have another minus here, because when you cube a minus 2, that's a minus a. So that's going to be another minus 64/3, I think. I think so. My brain isn't working too well right now. Okay. Now, then you have let's go back and redo that first one. When you plug the minus 2 in there, that's going to be a plus 32, isn't it? Because it's minus a minus 32, which is a plus 32. So those don't go out. Okay, so I think you're right. I think we can double them, but we're going to see in a minute. Well, I thought I had my eraser on, but I didn't. Nope, it's still not on. There it is. That one and that one can be erased. And then we have a minus, that one. So hard to see. Okay, now this one is a minus a negative 2 to the 5th, which is 32/3, so minus a minus. Yeah. So that's going to be another plus. So yeah, I think we could have just doubled it. Yeah. I thought that was the case, but I just didn't want to 32/5. Okay. So it would have just been double the 1. Now, this is a weird way to do it, but 6/5 of 32, that's 5/5 plus 1/5 is 6/5 of 32, and then this would be a minus 128/3. Goodness gracious. So hard to get it to be still. And a 1/2 out front. Okay? Now, take half of this, that'll be a 16, and half of that'll be a 64. I don't know if that's going to help things or not, but I think that's 96/5 minus 64/3. And if someone can do that on a calculator, I'd be most grateful, because I don't want to figure it out. Is that 256/15? I know it's a pain. I just can't stand looking at the screen. It's just driving my eyes crazy. So it doesn't seem like that's big enough.
What did they say it was?
Huh?
What did they say it was?
256/15. I think I botched up something somewhere here, but
256/16.
yeah. Is that what it got?
Yeah, that's just 16.
What's that?
256 divided by 16 is just 16. So yeah.
Okay. All right. Now, so you have 256 over 15, but that's divided by 32 over 3, because that was your mass. Remember, you're dividing by the mass. So don't let me forget that. And we can simplify this by making a 5 here. 3 will go into that. And 32 will go into 256. Is that 8 times? I think so. So that'll be 8/5. And you have row over row, which is 0. That's why I threw the rows away. So 8/5 is your, so that's 1 and 3/5. So somewhere about there. There's where your center of mass would be. 1 and 3/5 up here. That's the Y bar. X bar, of course, is 0. Y bar is an 8/5. So yeah, we could have eased our pain a little bit by doubling that. That would have taken care of the 1/2 and just on one side of it. That would have been much better. They did it the long, hard, arduous way as well. Okay. Now, what they get to is, since all these deal with uniform density, you'll always have the mass having that density and both of the moments having that density. So when you divide them out, they disappear. So after now, let's say, well, let's always count the density as 1, so we don't even have to haul it around. It may not be 1, but that's all we're going to divide out anyway, and it over itself will be 1. So basically, they ignore it from now on. That's why I was trying to ignore it myself. Now, that was a fairly, okay, let's watch how they did it and see if we can pick up any clues and make things a little bit easier on ourselves. But they start with, because you know the center of mass lies on the axis of symmetry, it's got to be x bar equals 0, and it is. Okay. Moreover, the mass of the lamina is rho times this, and they could have saved some effort there by going twice 0 to 2. Excuse me, but they do it, and you get 32/3 rho. I believe that's what we got to, wasn't it? I already erased it, but I think that's right. Yeah, I remember. And to find the moment about the x-axis, place a representative rectangle. They did it over here. It doesn't matter where you do it. Now, remember what you're doing. It's mass times the displacement, okay? The mass is the length times the width of this thing times its density. And this is 4 minus x squared times the width is your dx, okay, times your density, which is rho. That's the mass of this. And the displacement of it is your center of that, which is then exactly half of this. So your mass involves the entire rectangle, and its displacement upwards is going to be half of that. So that's where the alpha of x over 2 came from, and the 1/2 that we pulled on the outside. So your y sub I is going to be half your f of x. F of x minus 0 divided by 2. And that would be that part. And then you multiply that by your length times your width. So that's how you get 2 of those. So, and that's where the rho over 2 comes out here. And then you square this and get, yeah, exactly right. We've got 16 minus 8x width. That's that. And you integrate that, 16x plus minus 8x cubed over 3 plus x5 over 5 minus theta 2. And they magically say that's 256 rho, okay? And then you take that and divide it by the mass, and notice the rows go out, and you can divide this into that, that gave you 8, this and that gave you 5, so 8 is your location of your y bar. Now, my goodness, I never would have thought of laying it flat, but so you can balance it on the pinpoint, pencil point. There, that's exactly what you do. 1 and 3/5 up here, and on the y-axis, 0, 8/5. I've got another full calculus class for that blinking like that. That's not going to be fun. Okay. Glad this is stable. I wouldn't be able to look at that if it wasn't, but this actually is doing a little better now. Knock on wood. Okay. The center of mass of a lamina of uniform density depends only on the shape of the lamina and not on its density. For this reason, the X bar, Y bar is sometimes called the center of mass of a region of a plane or the centroid of that region. Just forget about lamina, planar laminas, constant uniform density. Just call it the centroid of the region. In other words, to find the centroid of a region in a plane, you simply assume that the region has a constant density of rows equal to 1. I mean, you can say rho is equal to 15/3. I mean, you can say anything, but if divided by itself, it's going to come out being 1. Compute the corresponding center of mass without paying any attention to rho whatsoever. Okay. Now, I think they're skipping an example, aren't they? They're skipping 2 examples. Example 5 and 6. All right. Let's see what we can figure here. Okay, I think this will be about our maximum amount of white space. Find the centroid of a region bounded by the graphs of f of x equal 4 minus x squared. That sounds familiar, doesn't it? And g of x is x plus 2. Okay. So what we have here okay, here's the max. Something like that. But g of x is x plus 2. There's the y-intercept of 2, slope of 1. So that's going to be the line that goes something like that. Okay? Where this is the point 1, 3. I'm hoping. 1, 3 will certainly be on this, because when x is equal to 1, y is equal to 3, x equal 1, y is equal to 3. Okay. So we looked into that one, didn't we? But we need the centroid of this. Hey. And it's this region here. Not this down here, that's the x-axis. No symmetry here whatsoever. Uniform density, yes, but no symmetry, no. Okay? Where do you want to begin? For everything we do, we're going to need a little rectangle, aren't we? Okay? Why not? Let's do the mass first. The total mass is going to be the integral from 0, minus 2 to 1. If we're doing dx's here, that fixes our this point to be minus 2 to 1. It's going to cover all the dx's in that, right? Okay. So that means we're dealing with dx's. Let me clean this up so it looks a little bit better. Yuck! Why is that eraser not picking up today? Well, there, it picked up everything. Okay. Minus 2 to 1. So that means it's going to be a dx out here somewhere. That's our thickness. Okay. Let's first just do the mass. And that would be the length times the width. And what's the length of this? This from here to here. 4 minus x squared minus, you got the minus g, minus x minus 2, right? The length of this is the y minus f minus g, okay? Top minus the bottom. That would be it. Now we can simplify that a little bit. It's the integral from minus 2 to 1. 4 minus 2 is 2 minus x squared minus x dx. What's the antiderivative of that? 2x minus x cubed over 3 minus x squared over 2, evaluated from negative 2 to 1. Okay, simple numbers, but more to calculate in here. Let's get it up here maybe. Put m is equal to, again, we're going to assume our density is 1, so we don't have to worry about that any. So this is going to be plugging in a 1. What do you get? 2. Okay. And then plugging in minus 2 is going to be minus a minus 4, which is plus 4, minus a minus, which is plus. A negative 2 cubed is minus 8 over 3. Buy that? Okay. All these minuses here. Okay. No, wait. I did it. I think I did it too soon, didn't I? I don't even know where I am. Oh, no, yeah, we get this. So the first one is minus a 2x, but with a minus 2 in there, that would be plus a 4. And the next is minus a minus a minus. So that's going to be 3 minuses, so minus 8/3. Okay? And then we have a minus, which is a plus, where you plug this one in, because that's squared. That's going to be a plus, if I'm not mistaken, plus 2, right?
Yes.
Okay. Woo-wee. All right. So 2 plus 2 is 4 plus 2 is 8. Now here we have minus 9/3, right? So that would be minus 3. And then we have a minus 1/2. So that would be 5 minus 1/2 would be 4 1/2, which we could write as 9/2. So there's our mass, or I sure hope it is. Yeah, there it is. 9/2. All right. Now, if it's okay, I'm going to erase the scratch down here because I don't have room to do it. So let's erase all this. Everybody got it? Okay. Trying to remember what that was. Yeah, okay, that wasn't anything. Okay. Now, what you want to do next? X bar or Y bar? It's up to you. X bar, why not? Okay. Well, it's not going to be all of X bar. X bar will be everything we're going to do up here over 9/2. Because we've already calculated what M is. So it's the moment up here. Now what moment do we use here? Well, In here is still the same thing we had before, the length times the width. Okay? But the displacement of this is just going to be x, right? Right? Because, so that's going to be the easy one. I sure wish I had done the y bar first, but y'all said x bar, so we'll do it. So this will be the integral from, again, we have to go minus 2 to 1. And here you have your, remind me what that was after all the things. It was 2 minus x squared minus x, wasn't it? That was the m part. Okay. Times x, that's going to be our, the x bar is the, how far from the y-axis it is, so that's going to be the, times x, and then times dx. Okay? So, I'm just going to do this integral for right now. Integral from minus 2 to 1 of 2x minus x cubed minus x squared dx. Let's do just that integral. And what do we get? Antiderivative of 2x, x squared minus, perfect, minus, and this will be from 0 to 3. No, goodness gracious, where did that come from? I have no idea where it came from. It's minus, I think I saw the 3 there, but I don't know where it got the 0 from. It's from minus 2 to 1. I guess I've translated everything once. I don't know. This is scary. So let's plug and chug and see what we get. The one part I can do, 1 minus 1/4 minus 1/3 minus negative 2 squared. So that's minus 4, isn't it? Plus I think it's a 4, isn't it? Yeah. Okay. And then a minus, and then another minus 8/3. I believe that's right. Okay. Let's see what we got. Plus 4 and minus 4 add to 0. This is most disturbing that we're... Oh, no, it's not. It's not at all disturbing. In fact, it's very... reinforcing that we better get a minus sign here, because look at this. All your mass is over here. It's not over there. Just a little bit's over there. So yeah, we better get it minus here. I was looking at that and say, oh no, we got a negative center of mass. So of course we do. Okay. So this is going to be, again, negative 3/3 and negative 8/3 is negative, 1/3 and 8/3, negative 9/3, which is a minus 3, plus 1, so let's say minus 2 and 1/4. Whoa! That's not encouraging. Oh no, that's fine. Because we're taking this, let's make this minus 9/4 over our 9/2. The 9's go out. 2 will go into that twice. This will be a negative 1/2. So right there is the x bar. Okay? At least I think so anyway. Yes, negative 1/2 looks like it's right. Okay? I know I just said it, but I don't know where I wrote it down. I guess I did. So negative 1/2. I just wrote it down here. Okay. So our x bar is negative 1/2. So all right for me to erase that? Okay. I am so hungry. Whew. Man. There, I think I finally got it all erased. So x bar is negative 1/2. Y bar. What will it be? We know it's over, over 9/2. So we know that part. But what's that numerator? I'll give you the limits of it. -2 to 1. And the dx is going to be out here. Now what goes in between that? Say again? Okay, x times x plus 2. Okay, how did you get that?
We use the same distance as we use for x.
I'm sorry?
We use the same distance that we use for the x.
Oh, okay. Oh, okay. All right, now, I'm not sure I followed all that. The inner part, the one part is going to be just like the other two parts have been, and that's going to be the dx times the height of this, which is just, is that what you were saying? Or? Oh, okay, okay. Yeah, I had forgotten what it was. So that part was, say it again, what you said? I remember there was a 2 minus x squared minus x, wasn't it? Okay, is that what you were saying? Okay, I'm sorry. My hearing's not good. Okay, so that part I know is in there because it was with this and the mass, the x bar and the y bar all use that part. The part that's here is the different part. What goes here? Could have been front or back, wherever it's going to be. The location here is going to be the middle of that. Remember? And how do we determine the middle of it? This height, we did this minus that. Remember? This part, we do what? The middle of it, the average of these two ends, right? How do you get that? This plus that divided by 2. The top plus the bottom divided by 2. That gives you the midpoint. That's going to be how far above you. You're going for y bar, so this one has one there, everyone would have one. So that distance of this mass above the y-axis, above the x-axis. That's the. So this will be your 1/2 of the sum of those. I'm going to put the 1/2 out front and do the sum of these, if my eyes will let me do that. Okay. 4 plus 2 is 6 plus x minus x squared. All right. And this is the real pain in the neck, okay? Because here we have to multiply two trinomials, and that's really an enormous pain in the neck. But let's do it. I was trying to think of some easy way to do it, and I can't. So let's just go to town with it. That's going to be a 12. Okay. I'm going to do the x terms next. 2 times x is 2x. Minus 6 times x is going to be minus 6x, so that's minus 4x. I think those are the only x terms we've got. So it's those two and those two. Okay. Now our x squared terms. We got a minus 6x squared, a minus 2x squared, that makes minus 8x squared. Okay, I'm losing the bubble here. A minus 8x squared. And then you have another x squared terms here, minus 1 more x squared, so that's minus 9x squared. Keep up with me, or keep me current here, because this is hard to see. Okay, x cubed terms. We're going to have this one times that one. That's a minus x cubed. And this one times that one, that's a plus x cubed. So if I'm not mistaken, those add to 0. Right? Then x to the 4th term, we have just a minus x to the 4th. Now, did I lose anything there? I think it all worked out. I sure hope so. This is what we're integrating from minus 2 to 1. That was a 12, so let me make sure they're in that dx. So let's do this up here. What does that give you? Antiderivative of 12? 12x. Minus 4x would be minus 2x squared, right? Yay or nay? Okay. Minus 9x squared would be minus 3x cubed. Is that right? And then minus x fourth would be over 5. Evaluate that from negative 2 to 1. Whew. All right. The one part is fairly easy. 12 minus 2 minus 3 minus 1/5. Not too bad. Now the minus 2 part, that would be a minus, a plus, times a minus, I think is going to be plus 24. Oh my eyes hurt. I'll try looking at this one and see if that will help some. Okay. That's, oh, this is a lot better. Minus 20, minus a minus 24 is plus 24. Okay. Minus a minus is a plus. And when you plug a minus 2 in, that goes plus, so that would be 2 times 4 is 8, right? Okay, plus 8. Now I got to look back at this and find it. Plus 8. Okay? That is a plus 8. Don't let me forget that. All right. Now we're doing a minus, which is plus 3 times a negative 8 would be a negative 24, right? Yay or nay?
Would it be positive 24 because it's a negative 3 times a negative 8?
Okay. Yeah, but because it's the bottom one, it's a minus from
Oh, okay.
yeah. So that minus times this minus is a plus, Then when you put a minus 2 in, that goes back to another minus, and that would be a minus 8 times 3 is minus 24, I think. Minus 24, which I'm going to right now get rid of with that 24. Okay. Then we have a minus, which will be a plus, and then put a minus 2, raise it to the 5th power, I think is a negative 32 divided by 5. Minus 32 fifths. Okay. Now let's see what we got. 12 minus 5, 12 and 8 is 20, minus 5 is 15. And here we have minus 33 fifths, which is a big boo hiss. Minus 33 fifths, which is minus 6 and 3 fifths. 15 minus 6 and 3 fifths. Help me, that is right, I think it is. So this will be 8 and 2 fifths, which I think is going to be 42 fifths. And divide that by 9 halves. Ooh, this comes out weird. Nothing simplifies here. So I think that's going to be 84 45ths. It can't be, can it? Yes, we can simplify that. 3 will go into each of those. We could have done this early on. 9 will go into 42, or 3 will go into 42, 14 times. Okay, that would have helped. She could have done it there, but it just seems easier to do it like this. And that would be then still not good, is it? Is that 28 15ths? You get 12 fifths. I must have made a dumb error somewhere here. But I'm not about to try to find it because I can't stand looking at the screen any longer. Probably in my subtraction or somewhere there. I don't know. But anyway, the book has it 12 fifths. And that's 2 and 2 fifths. So somewhere about there. So maybe right about here is where they have the center of mass to be. And I can buy that. You got about as much down here as you have up here. You got about as much over here as you have over there. So yeah, that is reasonable. So the X bar, can't even find it anymore. God. I know it's on the board somewhere here, but I'll look in the book. There's a negative 1/2. I know I wrote it somewhere there because I put it over. Maybe I didn't write it. That was the thing. So the X bar, Y bar is negative 1/2. And then what do we say it came out being? 12 fifths. Okay. I can't stand to look at that screen any longer. So let's see about example 6. Hopefully it won't be quite as nasty. Any questions on that before I leave it? I made a math error somewhere there. We weren't far off, but a little bit. Okay. Example 6. This is almost more geometry than it is math, or calculus anyway. Find the centroid of the region shown by this, and I hate it, they don't draw this. So this is going from 1 to 3, 0, 1, 2, 3, over 1, down 2, right 3. Let me get my axes in here. 0, 1, 2, 3. How far do they go? To 6, 4, 5, 6. Okay. Right to 4. Up 1 more to 2. And over here to 6. Okay. Say, find the, now what they say here, you may be able to find the centroids without resorting to integration. And this is one sample of that. This is a strange looking building, but it's all fairly rectangular. So split it into 3 pieces. Okay? And you could have done any 3 pieces, but these I think are the easiest 3. And they're 3 separate rectangles. And then basically do, the word I was trying to think of before was your diagonals. Okay? And where would that, the center of this one would be at 1/2, 3/2. Everybody buy that? Plain laminar regions, that would be half of this is 1/2 and half of this is 3/2, right? Where your diagonals intersect. Okay? So that would be the centroid of this region. Okay? This one down here would be these 2 diagonals where they cross, and that would be exactly halfway in between. So this would be at 5/2, 1/2. By that. And where these cross, that would be at 5, 1. Okay, that would be the centroid there. Okay. Now, they say using those 3, you can find the centroid of the region. Now, by the way, just a little note here. The centroid doesn't have to be in the region, especially when it's an odd shape like this. The odds are it's going to be somewhere in here, approximately. Maybe there. It may not actually be inside the region, and that's okay too. It's just going to be hard to have a pencil under it and balance it out because nothing's going to be there. But if it were there, that's where it would be. Okay? So, what are you going to do here? Well, you're going to treat everything as if these points have the total mass of your system, but what we have to have is the and they're reverting to area, which before we were calling mass, because it has a uniform density. So the area of this system, 1/3, this is a 3 square unit thing. This is a 4/1, which is a 4. And this is a 2/2, which is 4. So the total area of this, which you can think of then would be your mass of it, would be 11. How did they get 10? Oh, this is 3. Okay. 3 by, I can't add. 4 minus 1 is 3/1 is 3. So that gives you 10. That's how I've been doing today. So the total area is 10. Okay. So this is 3/10 of it. This is 3/10 of it. And this is 4/10 of it, or 2/5 of it. Okay. So you're going to weight them basically by those weighting factors, and that's what they use here your X bar is going to be 3 times this, that would be the weight of that one, 2/5 times 3 here, and 5 times 4 here. You know, how far it is, again, here's your axes here, okay? You placed it in this thing. So your X bar, this is basically your, they call it the area. Think of this as your mass, okay? That's your denominator. So your X bar is going to be the weight of this one, which is 1/2 times 3 plus 5/2 times 3 plus 5 times 4, okay? That's going to be your numerator of the X bar. This will be your denominator of the X bar, and so this will be 3/2 plus 15/2 plus 40/2. 20 is 40/2. Okay, so that would be 18. Well, let's just leave this 20. That'll be easier. This will be 18/2, which is 9 plus 20 is 29 divided by 10, which is 2.9. Almost 3. So somewhere right in here. That looks pretty reasonable for our X bar. Because you figured it's not going to be too far off from 3 because it's going from 0 to 6. And you have a mass here and a mass here. But this is a little bit more massive mass, but this is concentrated more here. So, yeah, 2.9 doesn't seem bad. I hope it doesn't. No, it doesn't. Okay, and let's see what the Y is. The Y bar is going to be 3/2 times 3 plus 1/2 times 3 plus 1 times 4. Okay, I got lost there for a moment. So this will be 9/2 plus 3/2 plus 4, I think. Okay, that's 12/2, which is 6, plus 4 is 10 divided by 10 equal 1. So right there is your center of mass. Just barely caught the surface. I said it could have possibly been above it. It just is on the surface. So maybe you could put a pencil there and balance everything there. It doesn't look like that would happen, but it does. Okay? So there, and we didn't integrate a thing there. So 2.91. Okay. Have we gone over? Why did y'all let me do that? Yeah, because I got another class coming up. Are they waiting outside? I had the pencil out here once upon a time. Did I put it back? Yeah, I did. All right. Next time, we'll start with theorem of Pappus. Goodness, that last bit went a lot faster than I was expecting. We almost finished the section. Do either of the odds, 5 or 7, both a calc chat. 7's a calc view. Do 9, it's a calc chat. 11 or 13, both a calc chat. 11's a calc view. Any of the odds, 15 to 27, all a calc chat. 15's a calc view. 29's a calc chat. 31 or 33, they're both a calc chat. 33's a calc view. 35's a calc chat. 37 or 39, both a calc chat. 37's a calc view. You can look at doing 41 and or 43. They're both a calc chat. 45's a calc chat. Any of the odds, 45 to 49, they're all a calc chat. 51 or 53, they're both at Calc Chat. 55 is at Calc Chat. 57 is at Calc Chat. And then we'll continue. Now, 7 finishes it up, so I'll try to have your test ready Wednesday, okay, on chapter 7.
Is it tomorrow Wednesday? Or next
Second.
week Wednesday?
No, it's day after tomorrow Wednesday.
Oh, day after tomorrow.
Yeah, all right.
Okay,
Yeah.
awesome.
All right, sorry I ran over. I'm really sorry I ran over because I'm not going to have much time before.